Good day. For those of you who hear me not in record but in live, it will be good to see you. If it's possible, if not possible, it's also okay. And also you can raise a hand and ask me if something will be changed or you want to ask questions. My name is Ruslan Shevchenko, and about what I can talk can be functional programming liberated from the Monadic style. I work at Robots Mom as managing partner, and we do R&D for ScalaUA, which work in privacy. So if you something startup. So problem questions. If you look at industrial code, then you typically see something like this. Map, then map, then map. Or maybe you see control flow, which reduces to linear, and control flow in DSL inside flow loops. So we have monods. But I really need this for fetching data, because this is a classical example of accidental complexity, which is not needed usually, because it should be like something like get and all. Can we change this? And maybe you know that in Scala exist few solutions for this, but it's not they're not mainstream. Why? And none of them are total. So the question is, can we make something new and great in dotty, which will be the next versions? So let's now think more, not so quickly and more systematically. At first, maybe I will go about short introductions about modern continuation concurrency and how this come to the current state of the industry. Then about constellation, and then I want to tell about project dotty async, when async await is implemented using task reflections. And here was few quite interesting questions. For example, what we do with high order functions when different monads. And at last, we will see task reflections in a non-trivial projects. No, I think that it is the biggest application of task reflections which I see. So monads, why we use monads for concurrency? If you want to understand how monads relate to concurrency, I recommend you to start with this article, which was published in 1933. In this article, author designed a simple concurrent evaluator for Haskell, where he defined a concurrent monad with operations. Then pure is semantic is submit to evaluator, map is semantic submit to value and function to evaluator, and we have input Q and evaluator. And flop map is submit value function, then submit the result. And on top of this monad, he built all concurrency primitives, fork, queue, and so on. And if you look at any effect library in industry, in Scala, then you will see in some cases the reimplementations of this library, but on different stages. Only one difference is that this evaluator can be different. It can be distributed. It can be one thread. It can be kernel threads. It can be enough free monad. But the basic design are exactly the same. Next question, which is quite interesting: why at all we represent this as monad? Why operation system can't do this? If we come to back at the beginning of the word, Then, sorry, 8 years before the zero time. Then we see one process, concurrency, when data between processes was isolated, and communication was provided by operation system entirely. Problem that context switching is slow. Memory mapping between is slow. So let's invent something new, something of unkind. So kernel threads. It was near the zero, and the most famous implementation is ScalaUA, which later will be was standardized. Where we will have many threads in one process with shared data. Problems. Context switching is still slow, and dealing with shared data is extremely hard. Okay, let's invent more fine kind. And the next step was Ruslan threads. Fibers was included in GVM 1.1 near 200, and now we have project loop, which, if all will be good, will be included in Java 15 or 16. So we have shared data, communication primitives, and scheduler provided by a library. But such languages as Go or Lang are happy with this, but in JVM, the history is slower, and in Scala. This was not coming to mainstream. Exist many interesting things why and results, but it's outside of our scope. Let's think what to do next. And the next was callback hell. Because developers think, oh, if we runtime or framework cannot provide us good interfaces, let we implement those interfaces by hands in our application code. And so it's all shared data and communication primitives use callback to avoid context switching in user, which was expensive in userland or very, very difficult and error-prone in userland, and expensive in kernelland. Then functional program monads is the some way how to organize these callbacks into something manageable scope. And now we have a Concurrency framework for functional programming, which usually have a scheduler, which are here to avoid callback, which are here to generate userland scheduling, which are here to avoid thread context switching, and which are here to avoid process context switching. So we have a long history, yes, and we see that concurrency can be, in general, it is work of operation. It can be, we can work with virtualized time, but not can for historical reason. So in general, implementation. So let's return to our monads. We have different, we can have evaluator, and we can have different types of concurrency in a free monad. And usually we have pseudo function, async and await pair of pseudo functions. Async is map from input to output, and we have await, which do monad and unmonad value wait until value will be ready. And we have some transformation, which transform function which use await to function which return wrapped in monad value and don't use await. So here is a main problem which we want to solve. In different framework, it's named different. We can see that it names async await, it names lift and lift, effectfully and bank. Because why bank? Because it is have bank notation from monad. And if you remember continuations, reset shift, you can also think about reset as async and shift as await. So runtime solution is Project Loom, and compile solution is our macros or control plugin. In Scala 2 exist many attempts to solve this. Here are the list. The first was Scala continuations, but it was very hard to understand the user. Scala async, looks like official solutions, but it is not support try-catch yet. It was a nice crowdness library from Prokopets, but it was research and it left research. If you work now, then I can recommend you sort work DSL, but it's complex, yes. And we have not some complex, but great libraries like Models and Effortful, but they are limited in functionality. It's very interesting why all this come in such way. And maybe one of starts that we have a fewer gap between research and between industrial program. And for one person come from research to industrial, it is too big. All these libraries use one of the two main techniques for transforming code into one style. One is state machine. You can see the example here. Let we have two async operations and state machine. What he do? He just keeps state as monad, and we when we need wait, we change state and the comma to switch and say call async operations and call me again, and I will be called a new state. So the next call will be here, then the next call will be here, and this is how it's work. It's such work in C# and Scala async, and most programming languages use this approach because it looks like more efficient. The next approach is CPS transform. CPS, it means continuation passing style. What does it mean? We have function, but instead function from one argument, and we pass the function arguments and what to do next, application, what to do next. So here we call do something, which process and call this function, which also do some processing and call own tail and up to count. So this is it. Usually it's stated that it is not very efficient, but what it's good that it's total. It can transform all program, and it can transform high level order functions, because usually we state machinist approach. Okay, we have dotty. It's a new compiler. They have clear and extremely new macro systems. Let's make ideal async transformer, which can be work. So project is dotty CPS async. You can look on it on GitHub, and it works with optimized monadic transform. It's work with any monad, which implements new facilities. It supports all the essential constructs of Scala language, and even supports high-order functions if we can write creative tag class for them. Let's look what is optimized monadic CPS transform. Again, here is our example, which one transform. And what we do, we work as CPS, but instead passing the continuation as parameter, we flat map the result to continuation. So just flat map without as a parameter. And here you see quite compact coder, and we see that we have here flat map and here map. Why? Because we optimize. We can optimize and remove unnecessary bounds, which was a problem for original CPS. Now let's think that we have sequence of blocks and how we will compose it together. If we have constant expressions, we will have poor. If we have two expressions which are synchronous, we can just use synchronous composition. If we have async and sync, yes, then async sync expression mapped inside async. And if we have two async, then we await. Very similar situation with variable, yes. If we have a synchronic variable, then we just leave it unchanged and transform tail. If we have a asynchronous variable, yes, then we processing the right side and then have a block with table. If you remember the memo about drawing all, yes, I guess that information is enough to be able to draw all for all other constructions because they are quite simple. Only one non-trivial case is while, because we have while conditions with body, and we transform this to recursive function, helper function, which transform conditions. No, we implemented all combinations of sync and sync. We look at a more complex case when we got conditions, then we check conditions, and if it's really continue, then we call us again in flat map as a current. And the example here we see version without all. Here we see small head of network service in written in abstracted way, and here we see a result which are unrolled inside in flat maps in the same way as human do it. I guess that for now, many people who know work with flat map, they write near equal code to this, because number of monads are usually of nesting are usually equals the number of awaits. But we can do this automatically. Okay, what do we need from monad? Well, of course, we need control flow, very much for flat map. For try catch, we need some notion of analog command error, which can be error or restore. And for integrations with other monads, which needed not in all cases, but it is fine to have such things. Yes, we have operations which allows to adopt callback style and wait for actions. Different monad can be in wide expressions if we have implicit conversions between those monads. So this program will work. And nice things, reminding yesterday talk of Jakub Kozlowski, if you have functor from monad to, for example, logged monad, then we can insert logging of monad breaks in by implementing, just by inserting logged on stop async. So, and all this stuff will be transformed to logged monad. Okay, what do we do with higher order function? Example of problem you here. We have for loop And for each word, we write something in channel. What to do? We think that for each operation, we can define a shift operation. How it shifted? It shift when original version accept function from input to output, then shift version accept one function from input to output wrapped in our monad. And our evaluator currently just transform for each on array ops to for each on shifted variant of array ops, which can be found. And if anybody provide some interface with high-level function, he can implement this or implement themselves or give the third party right to implement such shift variant. For example, for array, we just have definitions on our main things in array ops async shift, where defined for each high-level functions, shift version of these functions with two lists of arguments. One is array ops and monad, and the other are original arguments. And here, this version, as you see, it's return the monad, which evaluated when all inside was evaluated. We can provide shift version for Sonata library and blind lines for library authors. In theory, it is possible to generate a shift version automatically because dotty store a compiled AST for each method. But currently, we have no access to this from macros. We only can access this in rewriting tool. Maybe this will change it. And it is implemented and possible to make this in shift lambda functions. But interesting that it was hard to find real-world example of where we need third order functions, because on practice, when we say high order functions, in data programming, it's second order functions in 99%. But it is possible, and it is the case which is easy to make, but it is hard to find where it is. And in application code, we usually already have monadic version as business logic. So I guess that standard library and collections will be enough for most cases. Okay, and let's look at an example. Can we use our async await for something not async await, for something unusual monad? For example, a list. Let we have async await on space instead of awaiting on time. Here is an example. Is Knight tour. We have chessboard and we have Knight. Knight come to each cell and come to the origin place via backtracking algorithm. Can we do this? Usually we have class state. Let we think as Knight, let we are sitting, and we see state. We set we have set of next moves. Next moves, which will return list of status. And what are my algorithm as knife to do this tour? I do one of next status. Then if board is full, then if my point is original, then okay. Also, I can return empty nil. I can say, okay, so this is I can't manage in this fork on. So that will be empty list. And if board is not full, then I can do the same with the next states. So, and more forward and after the same already. And we see that quite complex backtracking algorithm, it becomes very simple with the using of such list monad. Current implementation situated on GitHub. I can see that it's quite a big part of work, and you can help by implementing business parts, providing small examples, or trying to use in own dotty experiments. Thanks for attention. And the last question is, okay, can we look how this is implemented in code? So here is the implementation. And it can be interesting as an example of dusty reflection. We have compile time only await, and we have async functions inline function which call macros. Macros, I will skip boilerplate, but macros what do, it's accept expressions which we have, and we have a long loop in which we transform each constructions. As we see in previous talk, we have quasi-quotations. On dotty quasi-quotations is also exist, but they are quite limited. And but if we have quasi-quotations, it looks like very easy. But for example, a try catch can be implemented, can be matched in quasi-quotations, or blocks can be matched because they use statements, but quotations work only with expressions. So we have, we can get from expressions tree, and we can do the next switch on all possible trees, which are then transformed. And then we have something like forest, where for each tree we have transformer. And let's look for how, for example, we transform block. So block, we have some function run, which have list of what's block. It is list of statements and the last expressions. Yes. So what we do, if we have definition, then we transform valid definitions as was specified at the beginning of the talk, or as the live sessions. If not, then we, for each expressions, do nested transformations, and then we apply with fold right all this transformation together with applying optimizations. And in such way, we receiving full CPS transform. And I can say that this was not very, and the main problem in such case is not that we have some fancy algorithm which are hard, but it's problem that Scala is a quite big language. But the most of constructions now works, and for example, things like here is example which was word count, when we have something like awaiting in channel is works, which looks like the main things is done, and all what is live is to fill a gap between experiment and industrial program, which is the looks of future. Okay, so you can download and play with this. If you play with dotty, then it will be very pleasant if you will play with this library and show me small examples which need more work or help me on missing part. Thanks again for listening. It's all for today.